All right, so let's go ahead and get started. It's my pleasure to introduce Prasad Raghavendra, who's here at Berkeley, and he's going to tell us about algorithms and barriers of intractability in high-dimensional statistical inference.
Hello, thanks. Thanks for the invitation. It's a pleasure to speak at an event in person after such a long time. It's even more bigger pleasure to talk about something that's really close to my heart right now. Today, and 2 lectures today and 2 lectures tomorrow, I'll try to talk about a few things that go between algorithms and also barriers in high-dimensional statistical inference. It's a very broad term, high-dimensional statistical inference. So let's see what I really mean, what class of problems I'm talking about. So here's a problem. I take n vertices, and I pick a random coloring of these n vertices into k colors. Okay, and after I color them into k colors, I add edges between them. In particular, for every pair UV, which have different colors, I include the edge between U and V with probability d over n. And so it's a Erdős-Rényi graph conditioned on being colorable, being a coloring. And then you erase all the colors and you get this graph. And the goal is to, given the graph, recover the coloring, even partially. Can we recover anything about the original coloring that created this graph? Okay. And that would be the recovery problem. And a weaker goal would be a detection problem, where you want to distinguish this graph from a random Erdős-Rényi graph of the same average degree. Okay, so that's a planted coloring problem. Here's another variant of the same problem. So here what you have is you have your vertices divided into 2 blocks uniformly at random. And for every pair UV, you add an edge between U and V with probability, which is d over n times 1 plus epsilon if they are between the 2 sides. So these are the 2 sides. And d over n times 1 minus epsilon if they are on the same side. Okay. And the goal is, given this graph, can we recover the coloring even partially? Okay. And for more importantly, for what values of the degree d and the epsilon can we recover this partially? All right, so this is quite a fascinating problem in that there's a lot of very interesting work that has been done on this problem. In particular, this is the landscape of what happens to this problem as you vary the parameters. So let's fix the degree d, and let's just increase the epsilon. So as you increase the epsilon, you're actually increasing the proportion of edges that cross the partition, and you're decreasing the proportion of edges that are inside the partition. Your graph looks more and more like a bipartite graph as you increase epsilon. So at some point, you actually hope that you can recover the partition. And in fact, there's a very strict transition that happens at this threshold called the Keston-Stigam threshold, which corresponds to a degree which is 1 over epsilon squared, exactly. D is equal to 1 over epsilon squared. Exactly beyond that degree, there are efficient algorithms that can partially recover the coloring that you started with. And just below that, it's information theoretically impossible to recover coloring.
Maybe I should say that your x-axis compared to my x-axis is the opposite. Like the problem becomes with you like easier as you move to the right.
Right. Yes. So my x-axis is usually like the signal. So as you move to the right, the signal strength becomes larger, and efficient algorithms exist to the right as you move. Okay. Right. So partial recovery just means that you find some assignment X, which whose correlation with the original coloring is half plus delta. For some delta, it could be 60% correlated with the original.
It's actually maybe the same because it's like the planted version. Like in some sense, it is the same. Like maybe
right. Right. Questions are good because I'm actually having difficulty speaking with this mask on. So it helps me take a breath. Okay, so all right, and in fact, there's a very beautiful algorithm. It's based on non-backtracking walk matrix. We'll get to all of this later. So if you go back to K communities, which is a planted K coloring problem, there are the issue becomes even more interesting because now there are two thresholds. There is a threshold beyond which it's information theoretically possible to detect, for instance, that the graph is not random. And there is another threshold beyond which efficient algorithms exist. And then there is this middle region where it's information theoretically possible. So if you spend exponential amount of time, you can recover the coloring, but it's conjectured to be computationally hard. So that's the landscape K communities. And for instance, if you look at the planted K coloring problem, this conjectured transition from easiness to hardness says that if and only if the degree of the graph is at least K minus 1 whole squared. So if K is 5, if the degree is 16, at degree 16, the problem becomes easy, and at degree less than 16, the problem is hard. So it's quite sharp transition and a quite a precise prediction of when the problem gets easy or hard. And for me, actually, this is one of the simplest average case problems that is actually is meant to be hard, just planted K coloring. And it has a very predictable transition too. Okay, so these we're talking about graphs so far. Next, there's a related class is CSPs. So I'll give you an example here. So planted not all equal SAT. So what's the situation here? We have n variables, x1 through xn. N variables, which are Boolean variables. Okay, and there's an assignment to these variables, which I've drawn here. And for every triple, ijk, if xi, xj, xk are not equal, then you add a clause with some probability. If they're equal, if they're all equal, you add a clause with a different probability. In particular, if you look at planted not all equal SAT, which is fully satisfiable, you add clauses only when the three variables are not equal. But this is a mixture where you add clauses with probably a higher probability if they're not equal and a lower probability if they're equal. Okay. So you have a constraint satisfaction problem instance after this, where I give you the clauses. Of course, you won't see the assignment. And your goal is, can you recover the original assignment, and how well can you recover it? For what values of this D and rho can you recover it? Okay. Okay, that's good. So, even for this problem, there's actually quite a nice prediction, which, this landscape is predicted basically by techniques from statistical physics, but, sort of this line of work was initiated by Krakala and Zdeborova. So they predicted this way to predict they hypothesized a way to predict these transitions. And if you use that for not all equal SAT, you get this nice picture. So the blue region is supposed to be easy. The white region is a mixture of where it's computationally hard or statistically impossible. Okay. And in recent work, we showed that when it's conjectured to be easy, there's actually is an algorithm to do it. So
why specifically is the not all equal predicate and not some other?
Yes, it's a great question. So we can ask the general question. The point is, let's look at general planted CSPs. I like to call them Bayesian CSPs because I just like the name. I made up. So yeah. So what's the general model here? it's you have a hidden vector which takes values from 1 through k. And let's say the hidden vector is sampled from a product prior, meaning each xi is sampled from some distribution mu over 1 through k. Okay. And then what you see this is your hidden vector. And what you see are linearly many sparse observations. So for instance, in community detection, you see edges. And you see an edge, you sort of get some information of whether the two endpoints are equal or not. Or it could be not all equal CSP, you see a triple clause, and you see that gives some information about the 3 variables involved. Or it could be just a single variable. Maybe you get the value of one of the variables, xi. Or maybe you get a value of one of the variable with some noise. So, but basically, you have observations which are sparse. They depend on constant number of variables. And there are linearly many of them. The key point is there's order n observations. Okay, and these observations come from a fixed number of types, right? So it could be not all equals, could be edges in a community detection or some other thing. We fix a set of types of observations that you make, and you get observations from that. Okay, I'm actually not going to formally define this model because it's just a lot of notation, but I hope you have a sense of what the model is. It will be good. So the way the edges are sampled, or the hyper edges are sampled, is just like an Erdos-Rini model. So depending on the value of xi, xj, xk, there's some probability c over n squared that you add a clause of type, some type between them, and you do it independently for every triple or every. So it's a general Bayesian CSP. So that's what I define. Okay, and for a general Bayesian CSP, you can ask whether you can recover X, can detect it from a random instance, and so on and so forth. Okay.
Maybe the way to think of it would be that you sample a hyper edge, and based on the projection of X to that hyper edge, there is a random variable Y over some set, which you don't know, and some set, some fixed set, and you get a sample from Y.
Yeah, exactly. Yeah, and you can use this thing to model many different things. For example, let's say you're doing planted not all equal set, and then you want to say, oh, I actually learned the values of some alpha fraction of the variables. Now, what happens to the complexity of this problem? Or you could say, maybe I have planted not all equal set, and every variable, I learned its value in a noisy way, meaning I got another zi bit for xi, another bit zi, which is noisy, and it tells you something about xi. Now, what is the recovery threshold? What's the detection threshold? So basically, it's a very general model. The only restrictions, again, the key restrictions to keep in mind are, I'm always going to be talking about linearly many observations. So there won't be any dense graphs. It'll be sparse graphs. It'll be order n sparse graphs and sparse hypergraphs. And it's always analogous to Erdos-Rini models of graphs and hypergraphs. Meaning, for every triple, there's some probability c over n squared that you add a constraint of type, some types, any particular type to it, and independently do it. So it's like an Erdos-Rini model of graph. Okay, so I like to show more pictures, just because, see, so the picture on top is what you get if you look at not all equal 3 sat and not all equal 5 sat, a mixture of not all equal 3 sat and 5 sat. The picture on the bottom is the predicted easy region and hard regions for like a strange variant of community detection. I think, let's say there are 4 communities, and you learn the first bit of the community labels, and then you don't know the second bit, and you ask, can you?
So in all these pictures, the white area is both the hard and impossible, and you don't distinguish between them?
Yeah, white in all these pictures, white is both hard and impossible, and blue is easy.
And it's always the case that the hard has non-zero measure. There is actually
no, we don't know. I don't know if in all of this. So let me be actually more clear for the audience actually. So there are two things that can happen in the white region here. One is that it's statistically impossible to recover. The other is it's computationally hard to recover. And the theory or that I'm going to describe, which is from Prasad, it doesn't tell you, it doesn't pertain to figuring out the transition between statistically impossible to computationally impossible. It's just the other transition, the transition to the left, which is between computationally possible to hard or impossible. Okay, so it's the.
When you say computational hard, evidently computational.
Evidently, yes. Yeah. So right. So that these are all hypothesized transitions, and that's in fact probably the most exciting part of this. That
the statistical one is not. Statistical one is not.
Yes. Yeah, that's right. So the computational ones are all hypothesized. Many of the statistical ones have been, of course, formally proven. The computational ones are hypothesized, and that's sort of what makes this a really interesting area for me, in that you have these very, very precise predictions, and we should either prove it or disprove it, right? So, any other questions on this? So okay, so I guess I already said this a little bit. So the question is, why these problems? What's so special about these problems among all the things? Well, I mean, the reason I chose these problems is, firstly, we love CSPs as theorists. CSPs give a very nice benchmark to test many of our algorithms and hardness techniques. So it's analogous to if you look at combinatorial optimization, there's a whole variety of problems in combinatorial optimization, but a lot of the focus is on max cut. And whereas there's a more important problems in practice, maybe price collecting TSPs or all sorts of combinatorial probability problems. The reason we consider max cut is because it's simple and we can prove things about it, and maybe it helps us make progress. So in a similar vein, for me, two community statistical block model, or just SBMs, stochastic block models, and this model of Bayesian CSPs is like the max cut of statistical inference. Of course, there are more complicated priors which are not independent and so on, which are important and interesting to study. But this is one way maybe we can make some initial progress. CSPs are great for reductions. If you want to do reductions, there's a whole theory of reductions for CSPs, which is at the base of this dichotomy conjecture, the gadget reductions. The second reason which I really like this area of problems is at least for this particular class of problems, there's a comprehensive and unified prediction of the computational transition according to statistical physics, at least for this thing. So, the work is cut out for us. Right? If you look at different problems, the predictions are still being made, or there's no comprehensive way to write down for a class of problems what is the prediction. But here it's very detailed and comprehensive, so it's a good thing to study. And I should add that one thing that's really missing from what I'm going to describe is there's almost an analogous theory around dense problems like spiked Wigner. And over there, the discussion is centered around approximate message passing as opposed to belief propagation. And there's analogous theory there. And I'm not going to touch on that because I understand EMP much less than I understand BP, which is less. So we won't talk about it, but I just wanted to point out that that's a big omission here. But for now, for these talks, for the most part of these talks, we'll talk about Bayesian CSPs. Any questions on this? Okay, so here's my lecture plan. So if everything goes as per plan, we'll talk about map estimates and a certain SDP hierarchy in this lecture. In the next lecture, we'll actually talk about belief propagation. We'll talk about how to draw these pictures that I showed you. And tomorrow in the morning, I hope to do like a theorist demo of sum of squares SDPs. And the last lecture, I just get to vent out about all my problems in life. all the problems that plague my existence. So it's good. Okay. So any questions? All right. So just to familiarize ourselves with this example a little bit more. Okay. So just to recall, this is going to be a model for a little while. So there are two partitions. There's this side is labeled +1, the other side is labeled -1. The edges between partitions are sampled with d times 1 plus epsilon over n. Within a partition, they're labeled with probability d times 1 minus epsilon over n. And yeah, and the goal is to recover x partially. Okay. Okay. So that's the problem. All right. So sorry. That was my rehearsal. Sorry about that. I have to reproduce it. Actually, let me not do that. Let's just continue with what I have here. Okay. So okay. So you have a graph G and sampled from stochastic block model. What is it that we really want to do? We really want to look at the posterior, which is probability of x given G. That's what we want to care about. That's what we care about. Probability of x given G is proportional to probability of x comma G. That's clear. It's just Bayes rule. So, and if I write down the probability that x comma G, that's this product here. So let P in be the probability that I add edges within the cluster, and P out is a probability that I add edges out across the cluster. So P out is d over n times 1 plus epsilon. P in is d over n times 1 minus epsilon. Okay. So you write down what is the probability of x comma G, which is it's given by this expression here. Okay. And basically it is proportional to this quantity here. And the key point I want to get to is that you can write down the probability of x given G in this form. It's a Boltzmann distribution. It's e to the power minus beta G of x. It's proportional to e to the power minus beta G of x, where G of x is essentially the quadratic form associated with the adjacency matrix of the graph. So it's just x summation over ij, xi, xj, ij in the edges of the graph. And the normalization constant is z of G, which is the partition function. And what is e to the minus beta? E to the minus beta is square root of P in over P out. The exact form is not super important, but the key thing I want to drive is that the probability is e to the power minus a quadratic function. The quadratic function is the summation x over ij, xi, xj, edges of the graph. Okay, so that's basically the posterior. And if you look at a neighborhood of this graph, how does it look like? Well, it looks like an Erdős-Rényi graph because you don't see the labels. Okay, if you look at just a neighborhood of a vertex in this graph, it looks like an Erdős-Rényi graph. In fact, if you want to generate a neighborhood of a vertex up to distance L, what you do is you start with a vertex, you pick a Poisson random variable whose expectation is D, and you sample that many neighbors. For each of the neighbors, you pick another Poisson random variable with expectation D, you pick that many neighbors, and you generate this tree. You should see a tree, and most neighborhoods are trees for any constant depth, and that's how the neighborhoods will look. So this is how the neighborhood of a graph of a vertex in these random graphs look like. And so as you can see, it looks just like as it would in Erdős-Rényi graph. And if you look at not all equal 3 sat, over there, how does the neighborhood look like? Well, you have a vertex. You sample a Poisson random variable with an appropriate expectation, and each of its neighbors will be clauses. You'll have clauses for every one of the neighbors of this variable. So this variable will participate in these clauses. And those clauses are, because not all equal three-sided, they have two other variables. Those will be some other variables which are not there in the picture. And then they will have Poisson number of neighbors, which are clauses, and so on and so forth. Okay, so that's how the neighborhood will look like. And if you saw the labeling also, if you saw the labeling of the vertices, then it will look slightly different. Well, how does it look? Well, you have a label for this vertex, which is plus. You sample a Poisson number of neighbors who's with mean d minus, and there'll be that many minus neighbors. And you sample another Poisson random variable with whose mean is d plus, and there'll be that many plus neighbors. And then you continue. This vertex minus will have Poisson d plus number of variables with a plus and d minus with a minus, and so on. So you just grow the tree. The only difference is that once you have the labels, you have two different Poisson random variables which add up to the original mean, and that's how the neighborhoods look like. Okay, so that's labeled Galton-Watson trees. All right, so
is this supposed to be the plus guys have a plus neighbor with high probability, and the minus guys have minus neighbors with high probability? Like, I was thinking that if that was the case, then you'd need a different d minus for the minus.
yes, actually, yeah, I think yeah, I guess, okay, I think I might have mislabeled the vertices here. The meaning
D minus is basically the edges that disagree in the column.
Yeah, D minus is the edges that go across, and D plus is the edges that stay within the cluster, and that meaning stays the same whether you're at plus or minus.
So the second layer is just
it's wrong, like the second layer is inverted. Like
second layer, this should be a minus, and this should be a plus. Okay, any other questions? All right, so now, okay, so let's get to work. So, okay, I'm going to talk about map estimate. What's a map estimate? Which is basically you find an x that maximizes the probability that x given g. Okay, it maximizes this e to the minus beta g of x, and in particular, it just amounts to, as I define it, just amounts to finding the max cut in this graph. Okay, it's really just finding max cut in this graph. So map estimate is just find max cut in the graph. Okay, so that's good because we know how to find max cuts. Let's just try to use Gorman-Williamson SDP. Okay, let's write down the Gorman-Williamson SDP for max cut and try to solve it, and use the value of the Gorman-Williamson SDP to distinguish between a random graph and a stochastic block model. Okay, and it's somewhat successful. So you can show that the Gorman-Williamson SDP works very well either if you're very well above the threshold, or it works as close to the case threshold as possible if you make the degree go to infinity. But we don't know yet if you can use the value of the Gorman-Williamson SDP to distinguish between the random graphs and stochastic block model. We don't know this yet. But there's an issue with this approach. The issue is the following. Let's throw away the Gorman-Williamson SDP, and let's say you computed the maximum cut using an exponential time algorithm. So given the graph, run an exponential time algorithm to find the maximum cut and look at the value of the maximum cut. We don't know even if that can distinguish between planted and random. And the reason is the following. Even if let's say you're in the situation where you're close to this threshold, even a random graph with no planted communities has a maximum cut which is larger than the planted cut on the stochastic block model. Okay, so let me, this fact took me a few months to believe, but so let me, it's a little surprising, but so this is a random graph and this is a planted. Okay, in the planted graph, there is a planted cut, right? That's called the planted cut X. Okay, so the planted cut has a value, max cut value or the cut value of the planted cut on this graph. You hope that because this is a planted cut, it must have a lot of crossing edges.
And we cannot know exactly what's the value, right? Because it's this epsilon, right?
Exactly, we know its value. Its value is exactly d times 1 plus epsilon over n or something. Oh, d times 1 plus epsilon n. So we know exactly the value of this, and it's a good. We expect that it's a good cut because. But what happens is in a random graph, there are all kinds of cuts. There are good cuts and bad cuts and very good cuts. The best cut in a random graph is actually has a value higher than the planted cut in the stochastic block model. The best cut in random graph has more edges crossing than the planted cut in this graph. It took a little while for me to internalize this. So
Or some range of parameters.
when you're close to the case threshold, let's say you're just above the case threshold, this is the issue. So what that means is that if you just use an algorithm, which is find the value of the best cut, and if it's more than the planted value, then use that as a distinguisher, does not work. Okay, that's a problem with a map estimate, in that it.
But will it still correlate with the planted cut?
Will it? Yeah, I don't know if it's known whether it should, but we don't know. I don't know if somebody has written down a proof that the best cut in
But it's believable.
it's believable. Yeah.
On the other hand, we cannot hope to recover planted cut perfectly, right? Because it's a very sparse model.
Yes.
So.
No. Right. No, but
He's looking at just distinguishing.
just for distinguishing, right? Yeah.
Got it.
Just for the distinguishing problem, the most natural thing to try is this sort of thing, and it sort of doesn't work. So it is believable that if you find the best cut in the planted world, it correlates with X, but I mean, you need to do a lot of, you need to prove it. We don't know how to prove it yet. And this brings back the question, what is the right SDP to do inference? I mean, we just wrote down max cut because it was a map estimate, but it's not clear if that's the right SDP that we should use to do inference. So here's another SDP, which I suggest. So yes.
Is it? I just checking the what's up. Is it? Do you know that it's not, or I mean, is the value of the cut of the max cut and planted higher than per random, or?
It's believable that it should be. We don't know. It's not written up. I think. Like maybe. I mean, I don't know how to prove it, but I'm sure somebody knows how to prove it. Maybe, and it's believable that it should be true, but it's quite difficult to analyze. In fact. Even yeah, I mean, so okay, I might be wrong here, but my recollection is that analyzing the value of the Gomans-Williamson SDP in a random graph is easier than analyzing the value of the true max cut in a random graph. And even for the Gomans-Williamson SDP on a random graph, the Montanari-Sane work was quite involved, and I mean, in fact, the way the Montanari-Sane paper works here is that it proves that in the planted world, the Gomans-Williamson SDP has a value higher than the planted solution. So in particular, you solve the SDP optimally, and the optimal solution is not meant to be the planted cut at all. It's something even better than the planted cut. It's some cheating solution better than the planted cut. But yeah, that's how it works. So Just something slightly unnatural about using this SDP.
By the way, here we cannot know exactly the numbers. The left-hand side would be like some the Parisi constant, so it would be something like advantage over half. In the left-hand side would be something like, I don't know, 0.67 over square root D or something like that. And then in the right-hand side, I guess it will be 0.5 over square root D when you're close to the...
Right. Yeah, so the value is, I think the value of the max cut is known for regular graph by Dembo and I think. But you know, all of these are very hard papers, so it's quite complicated. Yeah. So we want to write an SDP, and so what are the two criteria that I have in mind? Firstly, the SDP should help me distinguish a random graph from a planted graph. If I run it, it should be feasible in one, infeasible in the other. The second most important criteria that I have is that the thing that I'm looking for should be a solution for this. We're used to writing SDP relaxation, so the thing that I'm looking for, the max cut, is a solution to the max cut SDP relaxation. So I want that the planted cut should satisfy the constraints of my SDP, right? So the planted cut should be the solution to my SDP, and it should be able to distinguish planted from random. So what's the idea? The idea is very natural. So what is it? Well, firstly, the key point is that if I look at statistics, local statistics, in a planted graph, they all concentrate. For example, the number of edges that cross from left to right is some d times 1 plus epsilon over n, plus or minus order square root n. There's only like a root n deviation on that. For example, if I ask for what is the number of paths that go from, let's say, left to right, number of paths of length 2 that do this. Okay, that's some number with the order root n deviation. And same thing holds for all kinds of path. Any kind of statistic that you ask for, they concentrate. If you ask for how many trees do I have that look like this in the graph, well, that's going to be some constant times n plus root n. Okay, so that's good. So in some sense, for any acyclic graph, the number of copies of that concentrate. So the very simple idea is, we write an SDP which says the following, which basically says, find me a assignment X such that for every labeled structure with D labeled vertices and capital D unlabeled vertices. Okay, so let's say little d is 2 and capital D is 5. That means that if you look at any structure with 5 vertices with 2 labeled ones, right? I want the number of copies of such a thing in my SDP solution should be the same as what I expect. Okay. It's just going one step beyond saying, I want this many cut edges. It's just saying all kinds of structure. This is inspired by this influential work by Barak et al. On pseudo calibration. But so very simple idea. So now we have a hierarchy. Depending on what size structures on which I impose this constraint, I have a hierarchy of these things. And time to 3, right? Okay, 3. Okay, I might finish a little earlier, but basically the point is that every local statistics is a constant degree polynomial in X. So, for example, if I want to know how many copies of this are there in my graph, well, it's just some, let me call this tree T, some over all copies of T in my graph. Okay, and I want the left vertex to be, I want the left vertex to be plus and the right vertex to be minus. So it is 1 plus xu by 2 times 1 minus xz by 2, sum over all copies u, v, w, z. Okay. If you have 2 labeled vertices, it's a degree 2 polynomial in X. If you have little d labeled vertices, it's a little d degree polynomial in X. And so if it's degree 2, we already know how to write it as in terms of SDP, because it's just if you want to write this in terms of an SDP, it's just 1 plus, yeah, you can write it in terms of vectors, just like Gomans-Williamson. So we'll see more about the relation between polynomials and vectors and so on. Tomorrow we'll do sum of squares SDP. But this is a family of constraints that we can add in my SDP. Okay, and it's a hierarchy of family of constraints. Well, right now it is for distinguishing, but it's an SDP that you can write, and you can hope that you can use a solution to recover too. But okay, and what do we know about this? Well, we showed that if you look at this hierarchy, it's called a local statistic hierarchy. It has two parameters, 2 and D. As you increase capital D, you can do recovery as close to the case threshold as you want. Okay. And the key parameter, of course, here is the 2, which means you only have a degree 2 polynomials there, which means this is almost like Gomans-Williamson. You only have vectors. You don't have a sum of squares SDP hierarchy. So you can still solve it in quadratic time or maybe even near linear time. But it has a property that as you increase this capital D, you can solve detection as close to the case threshold as you want. Okay. And one nice thing about using SDPs is that you get robustness for free. So what is robustness? Imagine I took a stochastic block model, I changed epsilon and vertices edges in the graph arbitrarily, like a little of n edges in the graph. Well, why is an SDP thing robust? Well, basically, if I change only little of n edges in the graph, you can more or less say that the subgraph counts of length t, right? If you look at paths of length t, where t is a constant, let's say t is 100, paths of length 100, I change it by little of n. Okay. So all the subgraph counts stay the same. So if a feasible solution to the original SDP stays a feasible solution to the new SDP. The feasible solution to the original graph stays feasible even after you modify the graph. So it works, it sort of distinguishes between stochastic block models with adversarial noise on epsilon and edges and true random graph. Yes.
You mentioned this is quadratic time, but I'm a bit confused. Why isn't it for n to the d? It's just constructing this. I mean, read a number of such.
Right. So the thing is that since we are dealing with a sparse graph, if I look at a structure with d edges, there are only linearly many such structures. Because right, but actually, it's connected structures of length. Sorry, connected structures of length.
Okay, and you can find them in linear time.
Yeah, it's just
like n times d to the t, or like the degree to the little d to the power d to the capital.
Okay, because working out there's a constant number of neighborhoods. Okay.
Right. Yeah, and actually, really the proof. Look, I'd like to talk about this in terms of local statistic SDP hierarchy because it's kind of systematic, but really the proof only uses paths of non-backtracking walks of length t. The only statistic that you really need is really non-backtracking walks of length t. So really just paths of length t. It sort of makes sense because locally all the neighborhood every neighborhood is a tree, right? And so if you have only two labeled vertices, plus and minus, somewhere in the tree, sort of the rest of the dangling edges are sort of useless, more or less. And okay, so I'm thinking, yeah, capital D is like a constant.
The degree.
Oh, the little d is 2. Yeah, here it's little d is even 2. Yeah. So in fact, it turns out the 2 is enough. The degree. The degree of the graph is a constant. Yeah. The degree of. Oh yes, there are two. Sorry, yeah, there's two different little d's. Yes. So sorry, there's a graph degree is little d, and local statistic little d was the degree in x. But yeah. Yeah. Okay. Any questions? All right. So, all right. So we might actually end up stopping early, but it's fine. I don't want to start the next topic in the middle of a lecture, but okay. But before we stop, I wanted to list a couple of problems that are interesting. So one of them is this thing called verification. It's sort of a silly problem, but so okay. Firstly, we want to prove that this community detection. Eventually, we want to prove these assertions and prove that community detection is actually computationally hard in this region between Keston-Stingham threshold and this. So there's a region where we want to prove that the problem is computationally hard, meaning no efficient algorithm can solve this detection problem. But like, where does it go? Where does this problem stay? Is it an NP problem, or is it like, where is it? We don't have a good idea of this. So here's a verification problem. So you have a stochastic block model, and somebody gives you the graph and the communities. Okay, so you're given the graph and the communities. And what you need, all you need to do is to verify that the graph G is generated by the communities. Okay, it's an NP problem. So what does the NP guarantee? Well, if the graph is sampled from, if the graph and the sample is a stochastic block model, then output yes. Okay. And the key point is, if I take an Erdos-Rini graph, I take just a random graph, then there should not exist any choice of communities for which you output S. Right. So for all assignments X, if I give you, if I give an Erdos-Rini random graph and X, you should output no. Okay. So it's really the verification problem. If I give you the graph and the communities, can you verify that? Can you verify that G is a stochastic block model? Okay. And of course, for two communities, I think this is easy because, well, there's nothing interesting going on here because, well, the problem was impossible to solve up to a point, and then we have an efficient algorithm to solve. So there's no region where something interesting is going on. But if you look at K communities, then it's more interesting. So in particular, one thing that I should say is that the canonical algorithm that we have in mind doesn't work. The canonical algorithm that we have in mind is, just test if your cut has that many crossing edges. Like you expect P times 1 plus epsilon crossing edges, P minus 1 minus epsilon non-crossing edges. You just test that. That doesn't work because of the max cut reasoning.
I guess the quantifier is really that the problem is when X depends on G, right?
Yes, yeah.
The problem is that when after G you give an X.
Right. It's the NP adversary sort of thing. Yeah, exactly. If somebody takes a random graph and tries to convince you that it's a generated from 20, you should be able to distinguish that. Okay, and now, so
even in local statistic hierarchy, does that work?
Local statistic hierarchy works, right? So it works for above the K threshold. I guess my real question is, let's say you do the planted K coloring or the K community model, and you're just below the K threshold, just below the threshold where we know any polytime algorithms. We don't know any polytime algorithm here for detection because it's just below the threshold. In fact, the problem is supposed to be hard. But now if I tell you the communities, you should at least be able to verify it. Otherwise, it's a little bit unsatisfactory to me to talk about a problem that's hard when you can't even recognize the solution. Somehow it's like you should be able to at least recognize the solution if I showed you the solution, because that's what you're trying to find, right? So it becomes harder to, yeah.
Can I give you some extra information? Like, for example, if you give me you verify not just based on the communities, but based on the communities and the max cut related to them, right? Because we expect the max cut to not follow exactly communities, but right to be a bit better.
Yes.
But if you can verify based on that, would that not be satisfying?
Yeah, I mean, I think some such approach should work. In fact, yeah, I don't know. I mean, like even local statistics might work. Yeah, I don't know actually. Like even local statistics, one should expect works, but I don't know how to prove it.
So I'm saying that suppose you can't verify just based on giving the correct partition. But you can verify if I get the correct communities and the max cut associated with it, like the random variation that has like that.
Yes. Yes. Right. Okay. So I guess right, that corresponds to another thing, which is okay. The verification problem. I think there's another more general thing is, can you even certify? Can somebody show you some certificate that helps? And yes, the max cut can help. Yeah. I think if you show yeah. If you but basically, yeah, it's I don't know if a good algorithm. I mean, I think it's a workable problem, but I don't know if a solution to it. Yeah.
Do you think this verification problem becomes easier if we allow like the witness or the partitions to be slightly correlated and not just the exactly correct ones?
Yeah, I think.
In the yes case?
Yeah, I think if you allow for general witnesses, there should be a witness. Yeah, I think it's it should. I mean, I expect there to be a solution to this. But I just it's a good question to think about. I think. Okay, it's a little bit silly. Okay, so but it's a good thing. I mean, it's a little bit silly in practice, but actually maybe it's not silly in practice. Because if somebody shows you a community, you have to say, okay, it's good for me or bad for me. Otherwise, what's the point of finding communities?
Like even like statistical significance or something like that.
Yeah.
If the hypothesis of the community was generated based on the data.
Right. Yeah, exactly. Yeah. Okay, so this is one open problem. As I said, I told you I'm going to vent about all my problems in life. So here's another one. This one is simple. So it's sort of unrelated to what I've been talking about, but it's vaguely related. So here's a look at the following sampling problem. So the input is n. I just give you n, and I give you a clause density alpha, which is some constant. Let's say 2.4 or something. Okay. And what I want you to do is to sample a random 3-sat formula with alpha n clauses and an assignment, a uniformly random assignment to that formula. Okay. So I'm not giving you the formula nor the nothing. I'm just giving you a number n. I say n is 1000. Give me a random formula with 1000 variables and this many clauses, and along with it, a random assignment to that, a uniformly random assignment to that. Okay, so it's a joint sampling question, and you can ask this for any CSP, or you can even ask for planted problems. For planted problems, you have to be a little bit more careful. You have to say, give me a stochastic block model graph, and give me 2 choices of communities, because one choice of community is easy because I can sample X and sample G given X in the planted world. But if I ask you, give me G and X and Y sampled from the posterior, that's already a hard problem. And so this should be intuitively an easy problem, because the only input I've given you is n, right? It can't be Sharpie hard or NP hard or anything, right? It's just, I'm just giving you a number n, 1000, right? Like, give me a random thing like that. Shouldn't be hard. Yeah, I think you could, but I guess the key point is, like you can ask this sort of a joint sampling question for any of the models. In fact, random 3-sat will be like the amazing thing, but any of these models. And so why is this interesting? Well, it's interesting in practice for the following reason, I think. So statistical physics wise, let's say there's a conjecture saying, let's say the overlap gap is there at 2.4. At alpha equal to 2.4, 2 random solutions have an overlap of 0.7. There's some statistical physics conjecture. If you want to experimentally verify this, what do you need to do? You need to sample a 3-sat formula and sample 2 random assignments to it and check their overlap, right? And you don't care which formula. Nobody gives it. You want the formula and the assignments together. So if you want to experimentally verify statistical physics predictions, this is really the problem that you want to solve. So it is like a very basic problem. You should do it.
So for 3XO, would the natural planting just work?
For 3XO, I don't know. I haven't. Maybe it should. It should. I mean, for 3XOR, I think we should be able to do it.
It should be just two random things from the subspace, right? So it should be.
Yeah. I think, I think for 3XOR, we should be able to do everything that we want to do. But but I guess in general, even for 3SAT, I guess my point is that all the random walk literature and everything, you fix the 3SAT formula first, and then you try to sample it. And of course, it's a hard and important problem. But here, I'm not even fixing the formulas. If you could somehow sample the formula and the assignment together by some random walk or something, I don't know, it'll be amazing. And the reason I think it's really amazing, even from a theoretical point of view, is that like in traditional statistical physics way of understanding the solution space is to say, okay, at alpha equal to 2.4, the solution space shatters, and you prove the value of alpha is equal to 2.4 using some BP prediction or something very complicated, right? And you have the exact formula, right? Your exact formula for at the position of the threshold. A CS way of saying that we understand the solution space is that we have an algorithm to tell you the value of alpha, right? And this is like a CS way of understanding the solution space is to be able to do this. In particular, somehow, if you have an algorithm that solves this problem, that algorithm knows at what point the solution space shatters or anything like that, right? So the joint sampling question is a CS way of approaching these threshold questions. But I think it's just an interesting question. You want just to run it in practice because you want to verify a conjecture, you want to run this. Okay. And okay. And so I get paid. Oh, yes.
Why do you want 3SAT in particular as opposed to some other like KSAT?
Anything, yeah. Mostly 3SAT is an example here. The class of joint sampling questions is interesting. I think they should be easier than just really sampling, and I think they're interesting for it. It is an interesting open question. And I think for 3SAT and so on, this problem should be hard because implicitly you have to understand the solution space if you have to have such an algorithm. Like for example, you have a single algorithm that works for all n. Already you're proving that the limit exists as n goes to infinity implicitly because you have a single algorithm that works for all n, as opposed to even n, the threshold is something, odd n, the threshold is something. So it's tricky. So but yeah, so I get paid to think about these questions a lot. I get paid a lot to think about these questions, I guess. So I thought a more economical thing to try is to offer some of that money to you. So I'll promise to pay $100 for anyone solving this question over the semester. All right, so I think I'll stop here before we get on to the next topic.
So for clarification in your verification problem, if I give you A and B, the information theoretic threshold is still the same as before?
I think so, yes, because the knowledge of A and B should not change the, it's a subtle proof, but I think that's true. The information theoretic threshold doesn't shift.
Because I guess information theoretically you could enumerate maybe over all the potential candidates and run this algorithm, so you could distinguish if you had a verification maybe.
Yeah, but I think there's some subtlety in the proof itself.
If you have some kind of probability for the verification, then you affect the value.
I see. So
I guess it wouldn't be the case for, say, sparse regression, right? If you don't, like if I give you the unknown subset on which the true parameter is sparse, like the statistical rate is slightly faster than if you don't know this unknown subset information.
I think Yeah, so there is a a couple of semesters ago, the science program, and I suggested this problem at that time also, and there were some initial discussions on the topic, and somebody gave a formal proof that indeed information theoretic threshold doesn't show. It's a little bit subtle, but I think it was short but subtle too. There's some subtlety there. But, yeah.
Thank you.
More questions? Okay, so let's plan to meet back here in 20 minutes. We'll be at